Students, this lab activity is called gas, pressure, and volume inquiry. And in it, it's a really simple activity. We're going to use a LabQuest and a gas pressure sensor along with a syringe. Now, the gas pressure sensor is just this black box that has a port or a plug that plugs into one of the ports on the LabQuest. And we simply turn on the LabQuest. And what it will do is give you a pressure reading. So I'm going to be reading what the LabQuest gives me in units of kilopascals, which is a fine unit to work with, upon giving the air inside the syringe different volumes. Now, the air in the syringe, I can pull back on the plunger of the syringe and I can push it forward, but I want it right now to be drawn back about midway because we're going to take several different pressure and volume readings. I'm going to screw the syringe onto the gas pressure sensor, and right off the bat, when I have the syringe's plunger at 10 milliliters, I'm getting a reading of 101.8 kilopascals. So when you, in our data table, for the volume, you should record 10 milliliters and 101.8 for the pressure. Now, we're going to subject the air that's now trapped inside the syringe to differing volumes and then record the pressure that the machine gives us. First, I'm going to push down on the plunger. So I'm diminishing the total volume of air that is in the syringe. And as I do that, the pressure, as you might instinctively know, is going to go up. Because if I push down on a enclosed system of air, the pressure is going up. In fact, what I'm getting as a reading at 5 milliliters of volume, 204.1 kilopascals. So let's record that, 5 milliliters and 204.1 kilopascals. And as soon as I let go, by the way, the syringe plunger pulled right back into its normal position at 10 milliliters. Now I'm going to pull back. What if we give extra volume to the air in the syringe? Now, as I pull back and pull it back to the 15 milliliter mark, the pressure actually goes down. In fact, at 15 milliliters, I'm getting 67.5 kilopascals. So let's record that. 15 milliliters, 67.5. And then upon letting go, the plunger moves back on its own to the 10 milliliter mark. Let's see if I could go a little further. I don't want to go so far back that I pull the plunger out of the syringe. But boy, oh boy, do you have to subject a lot of pressure or a lot of force to pull that syringe back. Now I'm at 17 milliliters of volume, and I'm getting 60.0 kilopascals. So 17 milliliters and 60.0 kilopascals. Let's do one more. Maybe I'll pull back not so far this time. I'll just go to 13 milliliters. And at 13, I get 78.3. Let's record that. And we're done with data collection. Now for the fun part, we're going to use this data to make a really cool graph of pressure and volume data. So I'll meet you at the board. Okay, let's summarize the data that we collected. We just needed 5 data points. It kind of came quickly in that lab. When the volume was 10 milliliters, our pressure was 101.8 kilopascals. At 5, it went up to 204.1. At 15, it went down to 67.5. At 17, it went down further. At 13, as you might expect, it's somewhere between that. You would find at 10 and at 15. So we're going to make sense of that using a graph. Now we're going to ask you to do kind of an old-fashioned paper pencil graph. because a lot of good graphing techniques is based on that. Let's see, give me a better angle here. So let's take a look at this grid. I counted up the number of rows and the number of columns, and there's 10 each, 10 columns and 10 rows. And on the lab report, it says explicitly, we want you to put pressure on the y-axis and volume on the x-axis. So I'm going to go ahead and label that pressure on the y-axis. And our units were kilopascals. So we usually put in parentheses the units. And then volume in milliliters, which I will also put in parentheses. Now let's think about the data range that we experienced. Our lowest volume was 5 milliliters, and our highest volume was 17 milliliters. So if our volume is going to range from 5 to 17 milliliters, and if we have 10 columns, what seems to be a reasonable way to use up most of the space here is to have every column represent 2. So if it goes 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, and yeah, we go to 20, but that's okay. We're going to use most of the space on that grid. So we've got a workable scaling the axis here. That, by the way, most of the work of a paper pencil graph is scaling the axes. Now for the pressure data, the lowest pressure reading was 60 kilopascals. And our highest is 204. So we've got to fit all of that data into our 10 rows. I think what I'll do is, because we start only at 60 and not something smaller than that, I think what I'll do is I'll have every row represent 20, but I'll start, let's say, at 50. So I'll have my lowest pressure reading at 50, and then I'll go 70, 90, 110, 130, 50, 170, 190, 210. And yeah, I won't use the space above that, but that's okay. I still use the majority of the space on the grid. Okay, so now let's keep that in mind along with our data table, which hopefully you can see just above there. Yep, good. And let's take the data points from left to right. So now I'm going to use a red marker. We'll put a big dot that represents a volume of 10 and a pressure of 101.8. So on the volume, I'm looking like right here in the middle, and I need to go to 101.8. That'd be right about here. Put a big dot here. Next, I've got 5 milliliters. So now I'm going to be at this point vertically, and 204.1. So that'll be right about in this region. At 15 milliliters, I'm looking at this vertical line. We've got 67.5, so just below the 70 mark. Put a big fat dot. At 17, we have 60. So 17, I'm going to go smack dab in the middle of this box. And at 13, 78.3. So 13 and then 78.3 put us right about here. Now, students, you might say, okay, I can't quite see the relationship. Here are the only choices for you to consider. There's either a direct relationship, which is going to look like the line in math class y equals x, where it proceeds from the lower left of the graph in a straight line towards the upper right. Or you'll have an inverse relationship, which in a set of axes is going to look like this, which in math class is like the line y equals 1 over x. So given our data set, and I might even sketch in kind of the relationship I'm seeing here to help make that determination. Does that line that we sketched on the graph look more like this one or more like this one? Well, obviously, it looks like an inverse relationship. And that's the key point. This, students, is Boyle's law. Robert Boyle did a bunch of experiments on gases, measuring their pressure and volume, and very correctly determined that pressure and volume have an inverse relationship, which really set off a ton of new work in chemistry. Thank you for your good work on this lab.